Okay, we'll get started soon. So one quick announcement. So whenever you guys are having questions, please use the mic so that people online can also listen to the questions. And if you use the mic, I think it'll also be recorded. So that'd be helpful. With that, we'll get on with the second lecture by Professor Ajeet. I'll hand it over.
Thank you. So good morning, everyone. Welcome back to the second lecture. And this is about the theory of special Cosserat rods. So this, of course, naturally follows up from our first lecture yesterday on beam theory. And as you saw yesterday, that beam theory had several kinematic approximations. And we are going to do away with those approximations today. And therefore, this is also called geometrically exact beam theory. You know, many places you will see it being called geometrically exact. As far as taking into account the center line or the orientation of the cross-section is concerned, we do not do any approximation at the kinematic level. We do not linearize anything here. So we don't say, for example, sine theta is equal to theta or cos theta is equal to 1 or tan inverse of dy by dx. Yesterday we said it dy by dx. We are not going to say all those things today. Okay. So let me start with a cartoon. So this is our rod or beam in the reference state. And this then gets deformed. Maybe it becomes like this. And then you have the center line also. And of course, also the cross section. So this could, for example, be the corresponding to the cross section which was over here. So supposing this is at a distance s from the origin, then this cross section is this part of the cross section which was at s in the reference state. Okay. So the center line here, that's going to be given by the variable little r. It's a vector little r having 3 components because the rod can spatially deform. And it can deform in whatever way it wants. It can take a full circle also, unlike yesterday. Okay. So it's a function of arc length. Now, how do we take into account the orientation of the cross section? So to do that, we have directors here. D1 and D2. Well, let's not make it so big. So they are attached to the center line, and it signifies the orientation of the cross section. Okay, they are called directors. They are also functions of S only. So for cross section, we have these directors, D1 and D2. Now, there are different levels of rod theory. There are rod theories in which these directors are assumed to be orthonormal to each other, okay? Meaning they are unit normed and also perpendicular to each other always. And that's the theory that we will be talking about today. But there are also theories where the directors can change their length. This need not be unit norm. And the angle between them can also change. And that theory is called, instead of special, it's called general Cosserat rods. So this is called special because the directors are unit normed here and orthonormal. So directors are orthonormal. That's why we call it spatial. Otherwise, it becomes a general Cosserat rod theory. And D1, D2 then signifies the plane of the cross-section, the deformed plane of the cross-section. And therefore, it also signifies the orientation of the cross-section, okay? So I'll say denote the plane / orientation of the cross-section. Now, just because the directors are unit normed and also perpendicular to each other, that doesn't mean that the cross-section is not allowed to deform in this theory. Cross-section can still deform in this theory, but not in an independent way, as in the general Cosserat rod theory. I'll let you know why do I say that cross-sections can deform later on. So we have these kinematics, small r, and the two directors, which have to be orthonormal. And once you have this D1, D2, you can also construct the third vector perpendicular to these two. And because D1, D2 signify the orientation, D3 automatically signifies the normal to the cross-section. Okay, so D3 remains always normal to the cross-section. You can construct, so D3 is not an independent vector here. So you can construct D3 equal to D1 cross D2, which signifies the orientation of the cross-section. So with this, you then have a triplet of directors, D1, D2, D3, which are orthonormal to each other. Now, because they have to be orthonormal, so if we have to count how many independent variables do we have here? So in this center line, small r, this is completely independent from the directors. So it has 3 variables, for example. If you write it in a coordinate system, you get 3 components. So it has 3 independent variables. How many are there in these directors? Now, the fact that the directors are orthonormal, you can think of it as a map from one orthonormal basis to another orthonormal basis. So there will be a pre-image of these directors over here. And they could actually also be aligned with the coordinate axis, or it could signify the principal axis of the cross-section. Usually they are aligned with the principal axis of the cross-section. And then you choose your coordinate system in such a way that E1, E2 also becomes aligned with the principal axis. Okay? So here you have, let us say, E1 and E2, which are aligned along the principal axis of the cross-section. And this is getting mapped to the directors here, D1 and D2. And the fact that you also have E3 here, so you have one triplet getting transformed into another triplet of orthonormal vectors. Therefore, you can always relate them through a rotation tensor. If you have one set of orthonormal triad and another set of orthonormal triad, you can always relate them through a rotation tensor. And that's what we have here, therefore. So di of S can then be written as big R of S times EI. So big R is actually your kinematic variable here. And again, how many unknowns are there in big R? Independent unknowns. Big R is a rotation tensor. It's an orthonormal tensor. It has to satisfy the identity that R transpose R is identity and determinant of rotation is 1. Okay, so this is a rotation tensor. Big R transpose big R is identity and determinant of big R is 1. So again, it does not have all its components as being independent. So it has 9 components if you write it in a matrix form, but not all of them will be independent because of this constraint. Now there are several ways to denote 3-dimensional rotations. This is signifying 3-dimensional rotation. There are several ways to denote 3-dimensional rotation. One is called axis angle representation. Any rotation will have an axis of rotation and the amount of angle by which that rotation is happening. So then you can say, for example, this big R has the axis A, a unit vector A, and the angle of rotation theta. And mathematically, so this is physics here, rotation with an axis A, and rotation by theta. So this is physics here, but how do I write this mathematically? So this can be then written as exponential of theta times a skew symmetric tensor A. And how do you relate this skew symmetric tensor A with this vector A? These are not the same things, okay? Because you have see one arrow here, one bar here, and 2 bars here. So they are not the same thing. How they are related is any skew symmetric tensor A, when it operates on a vector V, you get this a vector A cross product V. And this is also called the axial vector of that skew symmetric tensor A. Okay, so all that you have to do is once you have this axis, the unit vector having A1, A2, A3, you then form your skew symmetric tensor from those 3 numbers. Because it's a skew symmetric tensor, if you write it in a matrix, you only have 3 independent numbers. So for example, if your A, if you write in a coordinate system having the 3 components A1, A2, A3, then the skew symmetric tensor A in the same coordinate system will of course have 0 on the diagonal, and then this is 1, 2 component, so it gets A3. This is 1, 3 component, so 2 is missing, it gets A2. This is 2, 3, so it gets A1. Yeah, the minus is now going to follow up. So, and then you have to put a minus here and also a minus over here. And then of course, because it's skew symmetric, you form it accordingly. So this is how you form the skew symmetric matrix from the axis vector. And that's going to come here and take the exponential, you'll get the rotation tensor. There is of course also a Rodriguez formula for rotation. So let me write that down. the same thing can also be written as cosine theta times identity plus sine theta into that skew symmetric tensor A plus 1 minus cosine theta times axis A tensor product A. Okay, so this is, I'm just talking about, it's a slight departure from what we had started with, kinematics of the rod. Now that we got this rotation tensor, I'm just talking about how that is usually represented. And there's also a reason why I'm discussing this now, because we wanted to see how many independent variables does it have. So when you see this representation, can you guess how many independent variables will a rotation tensor have? It requires one axis, which has to be a unit vector, and also the magnitude of rotation by which it is rotating. So it has 3, right? So because it's unit vector, so it will have 2 independent components and then 1 angle of rotation. So there are 3 variables sitting inside this rotation tensor. So for a total of, so small r having 3 variables and big R also having 3 variables, for a total of 6 independent variables in this theory. And as I said, depending on how sophisticated you want your rod model to be, if you want the kinematics to also capture cross-sectional deformation in an independent way, then you'll have more kinematic variables here. So that will increase your number of unknowns. From 6, it could go to 9, it could go to 12, depending on how sophisticated you want it to be. Okay, so now this is the kinematics. There's also, how do these kinematic variables relate to the deformation map of the underlying 3-dimensional deformation that is occurring here? Because you have this 3D, it's finally a 3D body which is deforming here. So you can also think of it as a 3-dimensional deformation. So there will be a deformation map F. So can we find what's the underlying deformation map corresponding to this small r and the directors that you have here? So, Antman had proposed the following kinematics. The F, the deformation map F, which is a function of the original material point variable big X, and which will have 3 components, big X1, big X2, and big X3, where big X3 is actually S here. So as you come down here, you have big X1, big X2, and big X3, and your S is aligned along big X3, so S is same as big X3. But big X1 and big X2 are lying into cross-section. Big X1, big X2, they denote the cross-sectional coordinates. They signify cross-sectional coordinate. So this map, how this was constructed is that you see that any point which is on the center line originally has big X1, big X2, 0, right? On the center line, it is simply SE3 originally. So that point is getting mapped to small r of S. The center line, SE3, is getting mapped to small r of S. So in this map, the first term is simply small r of S. Once you have x1, x2, 0, you just get this. Now, how do I take care of the points which are away from the center line? So any point, let's say, over here, which has the extra vector big X1 E1 plus big X2 E2. So this has big X1 E1 plus big X2 E2. This particular thing is small s E3 plus this extra vector. So you already took care of where is this point going. You now have to think of what happens to this vector. So yeah, so as you see that the cross sections are basically rotating here through these directors, and E1 is getting mapped to D1 and E2 is getting mapped to D2. And if you assume that the cross section remains rigid in this model, if you assume rigid cross section kinematics, then this distance is going to be preserved here. Whatever was the distance here will be the same over here. Also, if you have a straight line here, it will remain a straight line over here, if you assume the cross section to be rigid. So for rigid cross section kinematics, Antman proposed, which you can also derive geometrically, that you have this as plus x alpha d alpha, where alpha only goes from 1 to 2. You have a summation over alpha, but alpha goes from 1 to 2 only, instead of going from 1 to 3. This, of course, is then what is called rigid cross-section kinematics. Please interrupt me if you have some question. Which you can also write as small r of s plus x alpha big R E alpha. Okay, and then your x alpha being a scalar, you can move it anywhere, and then this becomes big R of s into, well, I should not put a bracket here, x alpha E alpha. So this part, as you see from this map, and as we thought also physics-wise, this vector basically has to be rotated through the rotation tensor big R. And that's what's happening here, where the center line is just getting translated. A point, the centroid of the cross-section, for example, it is getting translated through little r, and the cross-sectional vector, they are getting further rotated through big R. Okay, so that's the rigid cross-section kinematics, which Antman had proposed to just give a visual picture of how do these variables relate to the 3D continuum deformation map. But as I said, this is, you don't have to think that in this theory, cross-section is not allowed to deform. Actually, as you'll see later on, maybe in my last lecture, it also allows for an extra warping. But that warping is a slave to the local deformation. So this warping is not an independent variable. Therefore, it is not showing up in the kinematics over here. Okay, so this is also sitting there. Please do not think that this special Cosserat kinematics means that the cross-section has to be rigid. That is not the case. Okay, so once we have this thing, this in picture, yeah. Yeah, see this map that I wrote down here, this was just to visualize how do those kinematics relate to the underlying three-dimensional deformation. But this was just to visualize that. This is not exact, just to visualize. In reality, all that we have to say is that you have one small r and one big R as your kinematic variable. How it is relating to three-dimensional map, that is more deep or more complex. But just to give a basic idea, he proposed this kinematics. But this actually also allows, why is this happening? Why do I say that? Is because, for example, suppose you have a beam and you are stretching it, or you have a rod and you are stretching it, let's say by lambda. So your little r of S is going to become lambda S E3 if you're stretching by lambda. What happens to the cross-sectional variables? What is the underlying deformation map, little f, of x1, x2, and S? If you think of this kinematics, then you'll get lambda S E3 plus x alpha d alpha. And because it's a simple stretching, no rotation is happening. So d alpha is same as E alpha. So you'd come up with x alpha, E alpha. But is this does this happen? Because this means that your cross-section is not shrinking, right? But that does not happen. So if the special Cosserat rod indeed does this, it will get wrong physics. Where does it tackle the shrinking of the cross-section? We'll show it later on. Where does it come up? Therefore, I said that there is also a hidden U sitting here as a function of x1 and x2. Yeah. So this part was just to visualize relating the kinematic variables to underlying three-dimensional deformation map, which is quite deep. But if we can write down an explicit formula that helps us, and in that direction we wrote down this formula, or we wrote this formula. But then because it is quite deep, so you have also this hidden variable there. Okay, so this is all about the kinematics. Yes. Yes. Yeah, that's a very good question. So what you are asking is, this Poisson's effect, is this captured in the general Cosserat rod theory? So there are two ways to capture this. One is capturing independently. Another one is capturing as a slave to these variables, the small r and big R, meaning not capturing independently. So in the general Cosserat rod model, the cross-sectional dilatation is captured independently. Therefore, you have an extra variable. Whereas in this model, the cross-sectional dilatation is captured in a dependent way. We'll talk more about what is this dependent and independent thing later on when we talk about the constitutive relations for rods. Okay, so as far as kinematics is concerned, I'm going to stop here and move on to the balance equation. We'll come back to the kinematics when we find out what are the strain measures that gets invoked in this theory. Okay, so let's talk about the balance equations now. And you'll see that I will never use actually this kinematics in the derivation. Many derivations of special Cosserat rod theory uses this kinematics just up to this point. But because this is this is misleading, so I will never use really this kinematics in my derivation. Okay, now coming to the balance equation, So let's draw a segment of the rod. Whereas this cross-section was originally at S2, and this cross-section was originally at S1 in the reference configuration. So I'm just taking a segment of the rod. The actual rod is extending also in both the directions. So this is an arbitrary segment of the rod bounded by S1 and S2. And then we want to write down all the forces and moment, or all the external loads that are acting on this segment, so that we can do force balance of this segment. Okay, so on this section, this part of the rod is going to exert traction, right? Likewise, on this section, the remaining part of the rod is going to exert some traction. And then on the lateral surface, there will be some traction. Likewise, there could be body force. For example, if there's gravity, this rod could be pulled by gravity. So you could have body force acting all along. So this is obviously the 3D picture. The 3D picture of what are all the external loads acting on this segment. Now, let's look at the 1D picture of this, where we bring down all of these loads to the center line, and a statically equivalent load. Okay, so when you do that, you will see a distributed load acting on the center line. Let's denote that using this vector n with a cap there, n hat. Okay, and this is going to be a function of arc length s. At different s, you'll have different distributed load. And when you bring this down to center line, you will not only have the distributed load, you will also have distributed couple. Okay? You also have distributed couple. And let us denote that using m hat of s. Of course, this n hat and m hat, you can find out what they actually are from the underlying three-dimensional tractions and body forces that are acting on this rod. Because I will denote the forces here in the cross-section without hat. So yeah, without hat is for the force. Yeah. Okay, so once we have this distributed load and couple, you also have to talk about what's happening at the two ends, right? Because you have this traction distribution on the cross-section and also over here. So in this theory, we will have, let us define this NS as the total force that is acting in a cross-section. So N of S is given by integration over the cross-section of the Piola-Kirchhoff stress tensor P times the normal to the cross-section E3 d omega. So P times E3 gives you the Piola traction, which you then integrate over the cross-section to get your total force. Notice that this N of S is defined on a cross section with normal E3. If you have a cross section, or if you have a section with normal negative E3, then the force there will be negative NS, right? So on a section with positive E3 as normal, for example, over here, it has this normal, which was originally plus E3, okay? This normal was originally plus E3. So on this cross section, the force that is acting is N of S. You know, when you work with Piola-Kirchhoff stress tensor, the normal that you multiply to it is the original, the reference normal, not the current normal. Okay. So therefore, you know, you don't have D3 present here. D3 is the current normal, no? So you don't have D3 here, rather you have E3, the original normal, because it's the Piola-Kirchhoff stress tensor.
Excuse me, sir. So is it the first or the second, the Piola-Kirchhoff?
It's first Piola-Kirchhoff.
First. So N is, okay, so N, we take E3, but N is a vector on the like actual.
Yes, N is the actual vector, actual force vector that is there in the cross section. Yeah, this is often confusing to many people. Is N some kind of pullback, or is N acting in the reference rod? No, N is the actual force that is present here, you know, that is present here. The force that the remaining part of the rod is applying on this segment through the cross section over here. Yes. Yeah. Okay. Yeah, that's true. Okay, let me see how I can do that. So you have to really go back to the 3D continuum picture. You know, supposing this is your reference body, which gets deformed in this way. And then, let's say I want to know if you take a section here in the deformed body, okay? So this is, let's say, omega naught, and this is omega naught, meaning the reference body. And you have some surface here in the deformed surface, in the deformed configuration. And you want to know, when you cut this section here, how much is the force that is acting on this surface from this part of the body. So how do you get that? So maybe you write that separately. And then what is acting here is the Cauchy traction. You know, what acts here is the Cauchy traction from one part of the body on the other part of the body, Cauchy traction, which can be acting in any arbitrary direction. And this is given by the symbol T, T for traction, and it is a Cauchy traction, which is equal to the Cauchy stress tensor sigma multiplied by the current normal here, the current normal of the surface. Let us say that is N here. So T is equal to sigma times N. Okay? So on a small surface over here, you know, this is a big section. The traction T will be varying over the surface. But on a small part of the surface, on a small part, if one asks how much is the force, then that's simply, you know, because it's a small surface, I would say it is dF, the actual force that is acting on this small surface, which is sitting over here from this part of the body. dF is equal to sigma into N into D small s, where D is small. Okay, I should not have S here because S is for the arc length over there. So maybe I'll put A. Yes, thank you. So sigma n dA, where n dA is actually the surface vector. You know, surface can be thought of as a scalar, but also as a vector. Here, dA is the magnitude of the surface, and n is the normal to the surface. So n dA together is the surface vector, the tiny surface vector. So sigma into n is giving you the Cauchy traction, the actual distributed load that is present here, per unit deformed area. Traction is force per unit deformed area. Therefore, when you multiply with the deformed area, you get the total force. So this is the total force that is acting on this small surface. The problem with, this is very good, but the problem with this is when the body gets further deformed, and I want to still know how much is the load carried by this small surface due to the remaining part of the body. You know, this surface, that tiny surface, will have a different normal now. And the area will also change. Okay, we'll have a different normal, and the area is also going to change. The Cauchy stress tensor, of course, would have changed here. So the total force that is carried by this surface here, which was actually sitting on the big surface. So let us say this is your dF. I'm sorry. I don't know why it gets activated. So the total force present here will again be dF equal to sigma in this configuration. Let us say this is configuration 1, this is configuration 2. So you have everything 1, 1, 1, 1, dA1. Here, this is of course dF1, then this is dF2 is equal to sigma 2, N2, dA2, because that same surface would have changed its area, because it is deforming. It becomes dA2. The normal has also deformed. It has become something else. It was N1 here, but it is now N2. And of course, the Cauchy stress tensor would change. The problem with computing the force in this way is that you have to keep track of what's happening to the surface, that small tiny surface. What is the current normal? Is it possible that you can write the same thing in terms of what was this small surface originally over here, which will have some normal, let's say N0, and the area dA0. See, the force is still acting either here, or over here. But when it comes to computing, is it possible that you can do some change of variable, and instead of passing to it the deformed normal and deformed surface area, can we pass to it the original normal and the original surface area, which this tiny patch had? So can we write it as N naught dA naught? Because if you can do that, you only have to then think of what is the stress here in a current configuration. But as far as this N naught and dA naught are concerned, you don't have to track what is happening to that area as the body is deforming, because it is always in terms of the reference normal and reference surface area. So the idea is very good, but when you do this, you don't get sigma here. What you get here is P, the first Euler-Kirchhoff stress tensor. Okay, so that's the physics of first Euler-Kirchhoff stress tensor. You can relate P with sigma also. first Euler stress tensor can be related to sigma because the deformed surface and undeformed surface are also related. You can find out that. In fact, if I remember correctly, this is perhaps P equal to, can someone help me here? PF transpose. Is this sigma F inverse transpose? And 1 over det F? 1 over J or into J? Yeah, I guess it's going to be J. Is it into J? Divided by J? Multiplied by J, I guess, yeah. Where J is determinant of F. Okay, so I have helped you actually. You won't have to do so much. Okay, so that's how you get your first Euler stress tensor, and that's what is showing up here. And therefore, you have undeformed normal and undeformed surface area. So this is actually omega naught. Instead of omega, this is omega naught. So you're integrating over the undeformed surface, not over the deformed cross-section. But what you get finally is the actual force, which is acting here.
Sir,
yes.
I think it should still be omega because P dot E3 gives you a vector on the actual surface, right? On omega.
No, this gives you force, actual force per unit undeformed area.
Oh.
That's why it is Piola traction. This is not Cauchy traction. This is called Piola traction. So this is actual force per unit undeformed area. So you are integrating over the undeformed surface. So the domain is undeformed cross section. Okay, so that's your N. And likewise, you can also define M of S as integration over the surface of any point in the cross section, let's say X, minus little r of S cross product P E3 d omega naught. Notice that I didn't write this as big X alpha d alpha because I don't want to subscribe to this rigid cross-section kinematics. Okay, so I want to avoid that because that is sort of misleading. Whatever is the point X here, you find out what's the arm because you are computing moment about the centroid of the cross-section. So this moment is about the centroid of the cross-section. Cross product the little force and you integrate over the undeformed area and you get what's the moment carried by the cross-section here. Okay, so when you draw this picture here, you have this N, but you also will be having M. Maybe given by this little m of S. What's going to come here? This is, by the way, going to NS2. This is MS2 because this is at a section which was originally at S2. So N of S2, M of S2. Can someone tell me what is going to come here? What force is going to be present here? Sorry? Yeah? N of S1 minus N of S1, yes, because the section that you have here has its undeformed normal minus E3. When you put this with a minus E3, remember this N is defined for plus E3, but then what is there on minus E3 will come from the Newton's third law, exactly negative of that. Okay? So what's present here, you can draw the vector in whatever way you want, but this is minus N of S1. So this is signifying minus n of S1, this vector. Likewise, the moment is going to be there, minus m of S1. So that's the description of the external load that is acting in this segment, on this segment. So now you do force balance and moment balance, find out the equations. So when we work out the force balance, you have n of S2 minus n of S1 plus the integration from S1 to S2 n hat of S. So, that's the reason why we have hat. Hat is not denoting a unit vector here. The hat is just the distributed load that is acting externally. ds. That's the total force that is acting on this segment, and this has to be equal to 0, right? Any segment, if it's statics, any segment has to be in equilibrium. So now this thing, this is n of S2 minus n of S1. You could also write this as an integration from S1 to S2, n prime, where prime is with respect to S, ds. Isn't it? Because when you integrate a derivative, you get the same function evaluated at the end points. And that is what you have, n of S2 minus n of S1. Plus this thing. So I'll club them together, and this is going to be n prime plus n hat ds is equal to 0. And then comes what is called the localization argument, because this is going to be equal to 0 for any arbitrary segment, for any arbitrary segment, starting from any S1 ending at any S2. So this holds for any domain. This can only be true when the integrand itself is equal to 0. That's called the localization argument in continuum mechanics. So I'll put here using localization argument. What you get is n prime plus n hat is equal to 0. So that's one of the equations which we have derived for the rod. We then have to do the moment balance. Let's do the moment balance of this segment, maybe about the origin of the coordinate system. So think of the origin, which was over there in that picture, and your small r is going from there to the center line. So what is moment balance going to give us? Because it is statics, both force and moment balance should hold for any arbitrary segment. So you have actually the moments also there, distributed moment. So the total external moment due to distributed moment is going to be integration from S1 to S2, m hat of S ds. Then you have those end moments acting on the end cross sections at S2 and S1. You get m of S2 minus m of S1. Do we have anything else? Due to the forces also there will be moment, right? About the origin. So plus r of S2 cross n of S2 because of n of S2 plus r of S1 cross negative n of S1. So that negative can now come here. And we have one more thing. Due to distributed load, that's also going to generate some moment about the origin. That's going to be plus integration from S1 to S2, little r of S cross n hat of S ds. And this whole thing then has to be equal to 0. Okay, so what do we do after this? This is quite challenging to work out. As far as this is concerned, we can do the same thing that we did over there. We can write it as integral of m prime ds from S1 to S2. So you have, the goal is to write down everything as the integration from S1 to S2, so that you can then use localize an argument and find out what's the underlying ODE for the equations. So m hat SDS plus that is for the two terms here. In the same breath, you can also see that these two terms are evaluated at the endpoints S2 and S1. Just as you did for these two terms, you can do the same thing for these two terms. And you can write it as integral from S1 to S2 R cross N whole prime ds. And then the last term. Okay, now, there's some interesting thing going to happen here. There will be some cancellation actually. If you use chain rule here, this is going to become R prime cross N plus R cross N prime. So let's bring them all together, S1 to S2. And I'm also going to do some rearrangement. I'll write this as M prime from here. From here, R prime cross N. I'm going to put that here, R prime cross N. Plus this term, M hat ds. And then the remaining term, I'll write it separately. See, I have covered this, I have covered this, and I have covered one of them over there. The next one is R cross N prime. That comes here, R cross N prime. And also R cross N hat. So together, it's going to become N prime plus N hat ds equal to 0. It's not the scalar 0, it's the vector 0, because everything is vector here. And see that you have here N prime plus N hat, which vanishes due to the force balance equation. This goes away. And finally, you just have this term remaining equal to 0. And again, because this has to hold for any segment of the rod. So due to localization argument, the integrand must also vanish. And that gives you the second equation of the rod theory. Okay, and the first one was N prime plus N hat equal to 0. So this is coming from force balance. And this is coming from moment balance. Now, are these equations enough to solve the rod equations, or do we need something more? Yeah. Yes. Yeah. Yeah. No, because everything is with respect to the reference configuration. Everywhere the S that we had in the kinematics, for example, little r of S, that S is the reference S, reference arc length. Even in the force balance that we have here, these are also, the reference S, this n hat is the force per unit reference length, not force per unit deform length. Therefore, you are integrating in the reference arc length. Yes. Yeah, that's a very good question. So yeah, the primes are with respect to the reference arc length. I should write that down here. The primes denote derivative with respect to reference arc length. So remember that our original kinematics has 6 variables. And we do have 6 equations here. So is this going to close the system? It turns out no, because you have this small r sitting here, and this n hat and m hat is something which is externally prescribed, so it is not really an unknown. But then this n and m is also an unknown here. Okay, so you have to therefore somehow relate these n and m, which are also called internal contact force and internal contact moment. Internal because it's the response of the internal body, response of the body. It's not externally prescribed. It's the internal thing. Contact because when you cut a section, it's generating because of one segment being in contact with the other segment. Okay, so this is right here, also called internal contact force. Maybe I have that definition there. So this is internal contact force, just to know what it is really. And this is internal contact moment. Okay, so far you have gotten 6 equations, but you also have more unknowns sitting here, n and m. We don't know how do they relate to the kinematic variables. So that's going to be the next goal here. How to relate n and m. These are also called stress resultants in beam theory, because this is actually coming through integration of stress over the cross section. So therefore, they're also called stress resultants. To the rod's kinematic variable. So for this, we have to think of some energy function, just in the way we were doing that yesterday. And the energy function that we have here is energy per unit length. In our first lecture that Abigail gave, we had energy per unit volume, and Vincent introduced energy per unit area because it's a plate. Here, because it's a rod, we have energy per unit length. And to be more specific, it is going to be energy per unit undeformed length. Okay? So we have this function, let's say phi, which is going to denote energy per unit undeformed length. And we have to now think of what will this really depend on. So just as in 3D continuum mechanics, you postulate W depending on the deformation map and the gradient of deformation map, and further gradient if you think of higher gradient elasticity. Along the same lines, here, I'm going to think that this function, energy function, is going to depend on small r, big R, which are the kinematic variables here, and its derivatives. Just like in 3D elasticity, it depends on deformation map and the gradient of deformation map, which is the deformation gradient tensor. Here also, little r prime and big R prime. Of course, you can keep going, and you get higher gradient rod theory. But I'm going to stop here, okay? And it also has application if you have extra dependence. But I'm going to stop here. So for now, we say that the energy that we are postulating will depend on the kinematic variables and its derivative. The derivative is, of course, with respect to arc length here. Now, this is quite abstract so far. We have to really see what does it really depend on. Is it really going to depend on all of them or on some different combination? So that's the next goal that we want to address. So for that, we will use this principle of material frame indifference that is quite widely used in
Excuse me, sir, I
mechanics
have a
or
question.
mechanics.
Are these R primes, are they related to the director vectors in any way?
This big R is, of course,
Yeah, the R primes, no? Yeah.
The primes are DDS.
Okay. Are they related to the director vectors D in any way?
Well, this is, D by DS.
No, I mean the director vectors, D1, D2, E1, E2. Like.
That dependence is here, big R, not these ones. Maybe they are related to the derivative of the director vectors, not director vectors directly. For example, you have this DI equals big R EI. So directors get fully prescribed to big R. You don't need anything else. But DI prime, yes, that will require big R prime EI. So big R prime fully prescribes the derivative of the directors. Yeah. Okay, so we really want to see how does this really depend on. And for that, we are going to use this principle of material frame indifference. Which is also called material objectivity. So what this really says is that the energy of a deformed rod will not change if you superpose arbitrary rigid rotation and rigid translation to the deformed rod. So if you superpose rigid motion to a deformed shape, the stored energy will not change, isn't it? Because any rigid motion does not induce extra strain in the body. The strain remains the same, and therefore the energy stored will also remain the same. So that's the idea here. So how to exploit that, that is what we are going to do now. So we have this rod again in the reference state, which has gotten mapped the deformed state through small r and big R. Let us further rotate it, rigid rotate, by Q about some point x naught. Okay, so think of a point x naught here. And you are rotating this rod about this point by x naught. And that axis could be like this, it could be like this, it should be like this, and the angle also could be arbitrary. So all that is captured in this Q. Supposing that Q is about this point so that you can draw a picture nicely. So this rod is going to become something like this, just rotate it. When this happens, whatever was the energy here, you'll have the same energy over here, isn't it? Because it's a rigid motion. You can then further translate by some arbitrary vector t. So you just move it down. Or you can move it this way, you can move it that way. Let us say I move it like this. So this is the final shape, or this final rod. One is this here, and then you have this over here. Can we get to here through some small r, let's say nu, and big R nu? Can we find out what is that small r and big R, which will directly lead to this deformed rod, rather than going in stepwise, first through this, then here, and then here. So it turns out, yes, we can do that. So how do we do that? So think of this center line over here. That center line has to rotate and come here. So any point over here, that's the vector, and this gets rotated and is coming here. And here is your coordinate system, let's say. So this is your small r, and somewhere over here, that's your small r nu that we are looking for. Let us define this by small r the bar ever, small r bar. So can we find out what will be this small r bar in terms of the original small r? So notice that this vector is getting rotated. The picture is not really good because the length should not change when it rotates. So maybe I should move this x naught. The x naught we have here, okay? Because whenever vectors rotate, their lengths do not change. So this rotation is happening through Q. So this is originally small r minus x naught, which is going to become Q times small r minus x naught. So this is Q times small r minus x naught. Add to it your x naught. That will give you final r bar. So r bar is equal to x naught plus Q times small r minus x naught. Okay, so that's how you get R bar. And what is your R new? Once you have R bar, you just add T to it, the rigid translation. Okay, so R new is X naught plus Q into small r minus X naught plus T. So, originally that is what we wanted. Can we get here directly through some small r and big R? So your R new is this map. And where is the S dependence? So R new as a function of S. The S dependence is just here. Everything else, small x naught, Q, or T, they do not change with S. They are constant because it has to correspond to rigid rotation and rigid translation. Can you think of what will be big R new? We got small r new, but what will be big R new? What do you think? To find that, maybe think of how the directors are moving. So you have directors here, di, which has become di bar here. Okay, so here your di is big R ei. What is di bar? See, because it has rotated, so di bar you can get through rotation of di through that same map Q. So di bar is Q times di, which is Q R ei. So this is your R bar. That's your R bar, big R bar. And further, when you do rigid translation, it's not inducing any extra rotation. So big R new is same as big R bar, which is Q times R. So big R new is Q into big R. Okay? So I have to go back there now. And I still have some time. I think I can cover this up. Yeah. Okay, so what that really tells us is that the MO, material objectivity, or MFI, material frame indifference, this is telling us that phi of little r, big R, little r prime, big R prime, has to be same as phi of little r new, big R new, little r new prime, comma, big R new prime. Okay? Now plug in whatever is this new thing in terms of the original. So you're going to get phi of little r new. Can someone help me? What was that? Is this X naught plus Q? Yes, very good. Plus T, comma, Q times R. What will be R new prime? This is your R new. Take the prime. Q R prime, because these are all independent of arc length. We just get Q little r prime, comma, the last one. That's your R new, if the prime, it just comes here, because Q is independent of arc length. Now what do you think? If these two energy has to be the same for all T, comma, Q, how should the energy really depend on? Look at the first argument, for example. You have this little r. You can make it 0 by choosing some T, right? By choosing some T and Q, you can always make it 0. So this first argument sort of always becomes 0. So there should not be any dependence on the first argument then, because you are making the first argument arbitrary by choosing any Q and T. And the energy has to be the same. How can you have an energy depending on an argument which is same for any argument? It's only when it does not depend on that argument, right? So that's how the first argument goes away. Likewise, think of the second argument. You have this big R, and then you have this Q times R. In the same way, you are changing the rotation. This is a new rotation, composition of big R and Q. Here also, you are making this new rotation arbitrary by choosing any Q. How can you have a function which depends on an argument which is giving you the same thing for any argument? No, so these two really drop out. Okay, so what this tells us is that your phi has to depend on just the last two arguments. A similar logic also applies in 3D elasticity or 3D continuum mechanics, where you start with W depending on the deformation map and also the gradient, and then the deformation map dependence goes out because of this rigid translation and rotation. So you have phi of only depending on these two, but this dependence also has to be such that it's equal to phi of Q little r prime, comma, Q big R prime. So we are not done yet. We have to think of how really this energy will depend on these two arguments so that it does not change when you have this Q. So possibly you have to look for an invariant of this Q little r prime and Q big R prime, which does not change when you change the Q. Okay, so what are the invariants of Q little r primes and Q big R prime? As you change your Q, you have to look for an invariant which does not change. Now because the energy, what we're thinking of here, it's a local energy. It's not a non-local energy that we're looking for. That's again a different beast, which we don't want to look at. So assuming that it's a local energy density that we're targeting, you can choose your Q to be big R itself. What if you choose your Q to be big R? So choose Q equal to actually big R transpose. Whatever is the big R here, choose Q equal to big R transpose. Now you will say big R is a function of arc length, but Q is not a function of arc length. No? How can you choose Q equal to big R transpose? You cannot, but we are doing this only because it's a local energy function. So think of at a local point, whatever is your big R of S, take your Q to be same big R transpose. For a given S, and you can do this for every S one by one. Whatever is big R of S, take your Q to be the same big R of S, big R transpose, actually. If you do that, your phi is going to become big R transpose, little r prime, comma, big R transpose, big R prime. And it turns out, indeed, this combination is an invariant. This does not change when your R and big R changes in this way. Let's try to figure out, is that really the case? Think of this big R transpose, little r prime. This is going to change to big R nu transpose, little r nu prime, right? If originally you have this combination, finally it will be big R nu transpose into little r nu prime. But what is big R nu? That's Q into big R, right? Take the transpose. Little r nu prime. What is that? Little r nu prime. That's big Q, little r prime. So what you get is big R transpose into big Q transpose into big Q into little r prime, which is same as big R transpose little r prime. So indeed, you see that big R transpose little r prime does not change under that Q. Think of the same thing for big R transpose big R prime. This goes to big R nu transpose into big R nu prime. And this is going to become big R transpose into Q transpose into Q into big R prime, which is again big R transpose big R prime. Okay, so indeed, it is these two invariants that we are looking for. So finally, what we have derived is that your energy depends on, in rod theory, these two arguments. And these two arguments have very nice physical significance. Let's call this V naught and call this K naught. Okay. You see, this is because big R is a orthonormal tensor. This is going to give you a skew symmetric tensor. I'm running out of time already, I think, or I have some time. 2-3 minutes, okay. So big R transpose big R, take the prime, you get big R transpose prime into big R plus big R transpose big R prime, which has to be equal to 0, right? Because big R transpose big R is identity, prime of identity is 0. And this means big R transpose big R prime, this thing is equal to negative of this, negative of which is big R transpose big R prime transpose. So a matrix equal to negative of its transpose, means it's skew symmetric. Okay, so this K naught is actually skew symmetry. And therefore, you can think of a vector, the axial vector of K naught, with just single bar below. Because it has only 3 independent components, no, skew symmetric. So you can think of an underlying axial vector. What is this V naught? I think it will require some time. Maybe I should stop here. Okay, so I'm going to stop here, but I think if you have some questions, please ask me. Yeah.
Like magnitude of r prime square.
The dependence on small r prime, of course, that was remaining here.
So it need not couple with capital R. You can have something independent only with
No,
r
you
prime.
cannot have. That's what came out, no? If it is just a small r prime, it is changing to q times a small r prime, right?
But the magnitude is still invariant for whatever q.
Yeah, so the magnitude, so it can depend on the magnitude,
Yeah, so you can have
not on the vector itself.
No, I meant magnitude of r prime whole square, something like that.
So this is actually the magnitude. If you take the magnitude of V naught, you'll
But
see that it is
here
same as the magnitude of r prime.
But here it's coupling to the capital R, right? So those are 2 independent degrees of freedom in this theory, right? So,
Yes.
but
Yeah.
because R is always over rotation.
But it has many more things. It's not just the magnitude of r prime that is invariant here. There are many more things which are invariant. Therefore, you have 3 terms here. Otherwise, it would have been just magnitude of a small r prime coming here. You have 3 terms here. And you'll see in the next class that each of the components of V naught, and likewise the component of K naught, each of them has got a physical significance. Yeah. Yes.
When you eliminate the second argument, the one on big R, shouldn't this scalar product thing also work, or did they get lost?
Shouldn't what? The scalar?
If you take the scalar product, you should also eliminate the Q in the same way.
Scalar product. I mean, here again,
Yeah,
you can
you
take
get-
Q equal to big
Yeah,
R
yeah.
transpose,
Yeah, but
and
you
this
get
becomes
identity.
big R transpose into big R, which is identity.
Yeah, okay.
So this goes away.
Okay, I get it.
Yes, I have a comment on the when you arrive at phi as a function of r prime and capital R prime. Yes, so there is still. I mean, I don't understand the argument to eliminate R, because R it's still, you put R back at the end.
So again, the argument to eliminate.
So there is no, when you have the phi as a function of 4 arguments, you eliminate the 2 first.
Okay, yeah,
Actually,
so-
the second is still there at the
So
end.
what I really want to say is that it does not depend explicitly on big R. It has to depend on a combination,
Yes.
which is
Yes.
coming up here.
Sir, I have a follow-up to what I asked.
Yes,
So if capital R was 0,
yes.
You just
Capital R
have-
will not be 0 ever, because it has to be orthonormal tensor. It is identity when there is no rotation.
okay, so then it log.
Yeah. Determinant is equal to 1.
Invariants that you have given. So what does it physically actually like, how
What
can
does
we
it mean?
imagine that? Yeah.
That's something I'll cover in the next class.
For
But
both
I can-
the,
I can give a teaser to it.
Mm,
Yeah. So this V naught, if it has just the third component, that corresponds to extension of the beam. If it has just the first component, that corresponds to shear of the beam. Second component also is a shear. Then this K naught, the third component is twisting. The first 2 components are the bending curvatures. Yeah. Which we'll see more explicitly in the next class. Yeah. Yes.
Something that you dropped, right?
Yeah.
Would it be more explicit to see this, these deformations?
What you're saying is that if I put this U
Yeah,
and
I
then
think
work out
that-
everything.
yeah, and then look at the deformation.
Yeah, the thing is that U is not known. What will that be?
That should come from some energy minimization.
And also it's not a function of S, single variable, it's a function of X1, X2. So it's not easy to work with this if you keep it
Okay.
there. Yeah.
But there's no way by which these two.
We'll do that when we do the homogenization
Okay.
in the next class. We'll keep that U and find out what will that U be for the given choice of V0 and K0. So that's like, you know,
Okay.
solving the warping problem of the cross section. Yeah. Yes.
So can we find U using the volume constraint? I mean, the total volume has to be fixed.
Well, that's only for incompressible, no? What if
Right.
it's not incompressible?
So what we are dealing with the in
General, it's a general
yes.
body,
Okay.
yes. Yeah.
There are no more questions. Let's thank Ajeet again.
Thank you.